or k-wise independent distributions. And usually, when you teach a course in pseudo-randomness, you start with that. It's not at lecture 7. But that's only because it's easy. So, and easy is not my driving force. I don't care about interestedness. So, but it's definitely the case that if you remember anything from this course, this will be it. I mean, that's the main tool used for many applications. At the end of the day, sometimes just k-wise independence, pairwise independence is enough. And I'm kind of assuming I actually know that many of you know what these are. I'm not going to assume that, but I just know that because you answered my survey at the beginning of the course. But I'm kind of going to ignore that. And I'm just going to define k-wise independent distributions, or more precisely, k-wise independent family of hash functions. So again, I'm going to start with a definition, and then I'm going to talk about it, and then we are going to play with everything together. With this and with epsilon bias sets. It's another tool that we are going to combine with epsilon bias sets. Okay, so but the dry definition is as follows. And if you haven't followed the epsilon bias sets part or the Fourier part, then it's for today we are not going to combine them. So that's a good place to get back. So a distribution over functions from n to m. Maybe let's denote the distribution by h or hash. And it's like a cool h, like mathcal h, is said to be, and now I'm not sure I'm actually doing it correctly, putting the adjective in the right place. So I'm not sure if it's a family of k-wise independent or k-wise family of independent or so forth. So I'm just going to say one of them. K-wise independent family, maybe the family should be here, I'm not sure, of hash functions. But in slang, just k-wise independent. So this distribution is k-wise independent. If it's k-wise independent, so if for any x1, xk distinct in n, these are the inputs. So the variable, so the joint distribution of these variables is uniform over m to the k. Okay, so that's the definition. So you have a distribution over functions from n to m. And as usual, it's typically best to think of the uniform distribution over a set. Like when I say distribution, it's a bit abstract. And the best way to think about it, I'm just giving you ways to think about it. And usually, actually, that will be the case. So it's just a family of functions. Just a subset of the functions, not all functions. And you are uniform over, you sample an element in the set uniformly at random. But generally, it could be a distribution. Right, so this set is usually going to be much smaller than size m to the n, the number of functions that you have. But whatever. So that set or that distribution is said to be k-wise independent if you fix any k inputs to the function, to these functions, and you sample h from h. So you don't sample the input, you sample the function, okay? You take a random function from the family and you look at its evaluation, right? Each of them is an element in the set 1 to m. And you look at its evaluations like jointly, then that's going to be uniform. And it lives in m to the k, so it's a k tuple in this set. So that's going to be uniform over m to the k. Okay, so what really happens here is that you want to have a distribution that's not, so you have these like kind of related to Itai expression. You have like this marginal distribution that you're happy with. In this case, it's uniform distribution over the set 1 to m. And you want to sample n, not just one distribution like that. You want to have n samples of that indexed by this number from 1 to n. And ideally, you would have wanted all of these distributions to be independent, but that would be too costly in terms of randomness. So what this definition says is, now we're talking about samples and samples where every marginal distribution is okay, is uniform, but not only that, every pair and every triplet and every k tuple, up to this k that you are working, up to this parameter k. Okay? For example, pairwise k equals 2 is like pairwise independence, which is usually suffice for many things. And for pairwise independent, we just mean that when you sample h from h, and you fix like two inputs, maybe x1 and x2, then not only h x1 is uniform when you sample from h, but also it is uniform also given this one. It's just independent of it. Okay. Is the definition itself clear?
I hate the fact that it's called k-wise independent.
Me too. Yeah, I'll talk about
k-wise
uniform. Exactly. Good. So what Itai is saying, and I agree, but I have to stick to I don't have to, but I feel obligated to stick to the usual jargon in these things. So sometimes, and in particular in pseudo-randomness, by the way, the marginal distribution that you care about is not uniform. Maybe it's the output of a PRG. That happens a lot in pseudo-randomness. You compose things. And then you want to, so the underlying distribution that you care about is not uniform, and you want to make independent copies of it, or at least k-wise independent copies of it, and none of them is uniform. So the whole name, k-wise independent, when it only refers to the uniform distribution, is kind of misleading. And sometimes people call it k-wise uniform, and it's better. But I want to be consistent with like the usual literature, so I'll just call it k-wise independent, and we can all be angry about everyone calling it before, and me now that I joined these bad people. Like William Hosa, for example, in his survey that we are following a little bit here, also call it in the right name, k-wise uniform, and it makes it has some paragraph about why he hates the name as well, for the same reason. I mean, the other thing I don't like about it, and I was actually like against it for a while. I mean, I deliberately in papers I didn't write it like that. I never understood like why do you use these functions? I mean, for me, a better definition, now I'm kind of on the fence about it, would have been the following. You have this, you want n random variables. Each of them say is uniform. Let's stick with the uniform part. And you want these random variables to be k-wise independent and therefore uniform also, jointly uniform in k tuples. Why do you have to call these like functions, right? I mean, so these zi's, each of them is like say uniform over some set m, but why do you have to like collect them as a? I mean, it's weird. You sample the function, that's okay, but then instead of just calling it zi, you call it h of I. Like you have these n random variables, and instead of calling them z1 up to zn, there is a function h such that h of 1 is z1 and h of n is zn. And then it feels like it's kind of artificial because there is no function. These are just different random variables, right? I mean, if you want to output n random variables to work with n random variables, why name them as the output of a function that is given as index? Given us input the index of them and output them, right? It's kind of weird. I'm not sure I'm conveying the weirdness about this, but it's weird. And the reason usually people mention is that this way it is easier to talk about the complexity of generating them, because h is like a function, so you talk about the complexity of computing h and so forth. But I'm not convinced. again, I'm going against my will and following the usual literature because you don't want to just read my papers. You want to read other papers as well. Okay. Okay, so that's the definition. So let's construct.
But for this point, you would rather have it as a joint distribution of Z1 to Zn? That what
Right.
you...
Exactly. So the joint distribution would have been, well, not uniform, but any k tuple of the random variables there should have been.
The k marginal
The
is...
k marginal, exactly. The k marginals are correct. That's what I want usually. Even if it's not uniform, they're just correct. They're independent and marginally they are the same. Right, I don't really like this H because it's kind of collect things in a... Sometimes it's used, sometimes it's actually quite natural, but in many cases it's not. You introduce this H when you don't even want to refer to it. You want to refer to the variables. So, you can keep both in mind after you get used to one of them, but you should start with one of them, and let's start with this presentation. It's the same thing, just kind of, burning fuel here. So I think that the best thing to do with KY is independent initially is to construct them so that you'll get what's going on. So maybe even before that, can you maybe, oh, that's ugly. Can you see in the context of PRGs, these are PRGs of what? Like, what do you feel? I don't know if you know the name even actually.
Functions or only looking at k variables?
Exactly. So these are PRGs for what's called kind of K juntas. Like a junta is like a small group that control everything. So if you have a function that it's on n variables, like technically, but it actually depends on only k of the variables, it completely ignores the others, then that's called a K junta. And these are PRGs for K juntas. And with what error?
0?
0, exactly. So this is a 0 error. Like this is the epsilon, right? This is a 0 error PRG, so it's kind of weird. Usually you don't have 0 error PRGs. So this is a 0 error PRG for K juntas. That's in terms of PRGs, if I'm trying to put it in this context of pseudo-random generators, the K1 independent distributions are 0 PRGs for K juntas. But it's not, I mean, you shouldn't think like that about them. It's like you do more with K-wise independence than thinking of them as pseudo-random generators. Yeah, as we will see. Okay, so let's construct K-wise independent distributions. And actually, it's kind of technically annoying to do that because there are two parameters here. I mean, there's K, that's fine, but there's just N and M. And the easiest way to start constructing K-wise independent distributions is when N equals to M. And then you can tweak it a little bit. So I'm going to construct a K-wise independent distribution when N equals to M. And if you want, and sometimes that's the case actually, but if you want M to be maybe 0, 1 and N is large, or sometimes this is small and this is large, then you can tweak it by either ignoring or padding with zeros the construction I'm doing. Okay, so that's a little exercise. I won't even bother putting it in the homework because it's just annoying. But you can look at Salil Vadan survey and then it just mentioned how you can tweak what I'm going to tell you now, namely a construction when n equals m to a construction where n and m are anything can happen there, and you don't pay anything. I mean, it's the same thing asymptotically. I'll mention that a little bit actually. There is some payment, but I'll mention it at the end. So let's construct a k-wise independent family H, and it's going to be actually, as I told you, from n to m. And in fact, I'm going to assume that n and m, which have the same value, it's a prime power, so that I can look at a finite field of that size. right? So you don't have finite fields of every size, but if the field size is, if n and m are prime powers, then you can get you can find, I mean, there is a finite field of that size. There are, by the way, some issues also with the epsilon bias sets. Every time you use small fields, finite fields, there is an issue with efficiency, because really to work with a finite field, you need to like have the kind of the multiplication table of the field. If it's a prime field, it's very easy. You work modulo p. But if it's an extension of a prime field, like f2 to the n, then that actually starts to become more annoying. And in some cases, when the characteristic is small, there are ways of doing that, and in others, there aren't known way of doing that. I'm kind of hiding it under the rug because these are never really important. But I should say that, in terms of explicitness, I'm writing an F here as if I can, computationally use it as I wish. But technically, it's more annoying, and I'm hiding it. And also, again, in Vadan server, there is this paragraph about that as well, if you want to read it, even a full page. Okay, so I'm going to construct a k-wise independent distribution from F to F. And what do you think? What I'm going to use for that?
Polynomials.
Polynomials, right? Once you do this, there's only one way to continue with polynomials. So my set of functions, so as I told you, you should think of the distribution as a set of functions usually, is going to be indexed by a k tuple. Okay, so I'm actually slightly elaborating on this set, where this tuple, all of these elements are from F. So even before we start, what's the seed length? Even before I analyze anything.
The number of points, the A0 to A1.
Right, but I measure in bits, so
times log, n.
exactly, log n, yeah, exactly. Which is also k log n in this case. Right, I mean, I'm going to, I haven't told you what the construction is, but I told you how I'm sampling from the set. I told you the set. I mean, I haven't told you the set. I told you how many elements are there in the set. There are f to the k. So the seed length is k log f, which is k log n or k log m. That's not so bad. You like logs. It feels bad that k is like not inside the log, but that's unavoidable. I mean, why do you have to have k log m in general, regardless of n or dependence? Why do you have to have k log m random bits in your distribution? Okay, so if you look at a k tuple in the output, right? So the only randomness that generates this randomness is the one that you fed here in the seed, right? And the output, a k tuple in the output is, the output symbols are of size m. So the output randomness is k log m, right? In a particular k tuple, forget the fact that there are many k tuples, but for any particular k tuple, you have to have at least k log m random bits sitting there because you need to be uniform over m to the k, right? And that's the only randomness that's fed into the system. So the seed that you are putting in must be at least k log m, just to make sure that you have enough randomness to be uniform in a k tuple over m, right? This doesn't explain why there should be a k log n, and indeed there shouldn't be a k log n. If I remember correctly, the optimal seed, I'm not sure, I should check, is like log n plus k log n. But I'm not sure. I'll check, okay? Okay, but anyhow, let's continue with our construction. This was a side. So the CNF is not quite on a side, but that's on the side. And okay. And what's the construction? Well, I just need to specify this function. So, what do you think I'm going to do? There's only one thing I can do here. What do you think I'm going to do?
The polynomial that is defined by, like, the k minus 1 degree polynomial defined with the coefficients.
Exactly. So given the coefficients a, which I wrote as a vector here because I'm lazy, this is the way I'm defining this function. It's indeed from f to f, and we are happy, right? This is a polynomial in one variable. Good. So let's see, why is it? I mean, it's kind of it smells like Reed-Solomon, right? I mean, something Reed-Solomon is happening here, but actually, I don't think that's the way to think about it. I think that it smells like polynomials, and Reed-Solomon and that are. I mean, you can relate them one to the other, but actually, it's kind of there is an underlying reason for both. You can also see this if you saw Shamir's secret sharing scheme. It's also one of these things that polynomials are really good at doing. But let's see. So why is this? Why is h ky is independent? Well, let's follow the definition. The definition told us that we should take k distinct inputs, namely k distinct field elements, and sample h uniformly at random. In our case, sampling this vector of a's uniformly at random, and see what happens. How does the joint distribution looks like? So let's do that. So let's fix x1 up to xk in f. It's supposed to be n, but in our case f is n, distinct. I mean, I don't expect a random variable to be independent of itself, so distinct random variables. And I want to ask, so I ask, what about the joint distribution h of x1, h of xk, where h is sampled from h. So namely, h. So really that boils down to sampling the vector of coefficients a. And if I want to show that this is uniform, then really what I should do is to kind of look at a potential output, maybe let's call it b1 up to bk, and ask what's the probability of this to be equal to b1 up to bk. Right? So really what you want to prove is the probability that this tuple is this particular value. So that's a particular element in f to the k. And this f is actually m, but f is m. You want this to be what?
One over m to the k.
Exactly, but I'll do this. Yeah, you're right. It's m to the k, but I'm going to do just f because I paid my dues here when I mentioned that. Right, so that would mean that this is uniform over f or m to the k, right? Because every output is hit with the right probability. That is the definition of uniform. Okay. So let's see. So what is h of x? I mean, I'm writing h sampled from h, but actually it depends on a. So h of x1 is a0 plus a1 x1 plus a k minus 1 x to the x1 to the k minus 1. And I want this to equal, I'm asking, what's the probability that this is b1? And I want that h of x2, which is again a0, when I sample these a's at random, I mean, then I'm just analyzing that, but I'm just writing it now. x2 plus ak minus 1 of x2 to the k minus 1 is b2, and up to the kth one, right? So I'm just opening up the definition of what are the h's. So that event occurs exactly when these hold, right? Like with the ends. Okay, and remember the things that are like running are the A's, right? The X's are actually fixed, the B's are fixed, and the A's is the randomness. The randomness is actually coming from A. So a better way of writing this, so that's equivalent to saying that, let me be careful here. So 1, x1, x1 squared, x1 to the k minus 1, 1, x2, x2 squared. I'm just writing it in matrix form because you see the x's are fixed and the b's are fixed. The only thing that's alive is the a's, and these are linear functions in the a's, right? So I'm writing it as a linear system. 1 xk squared, xk to the k minus 1 times what should equal what?
Times A should be B.
Exactly. Unfortunately, the A's are indexed from 0 and the B's are indexed from 1, but you know. Good. So saying this, I want to ask what's the probability of that to happen, right? Is saying that. So I'm asking what's the probability with respect to A. I mean, everything else is fixed. These are fixed. This matrix is fixed, and this vector is fixed. This goal, like matrix is vector is fixed. And I'm asking with respect to A, like when I sample an element from A, this K vector over F, what's the probability of this to happen? So can you see an old friend here sitting?
Van der Monde.
Exactly. So the point is that this matrix, called the Van der Monde matrix, is non-singular, right? So this means that really this operator is a bijection from f to the k to f to the k, right? It's 1 to 1. So for every b that I'll plug here, there will be exactly one a that will be mapped to it. So the probability of hitting this is exactly 1 over f to the k. Right? That's what you want to prove. You want to prove that the probability of hitting this vector is 1 over f to the k. But saying that is equivalent to saying that, and asking what's the probability with respect to the a's for this event to hold. And the point is that, for every fixed b, after you fix the x's, there is exactly one input vector that will map you to that output vector out of the f to the k vectors. So indeed, it's probability 1 over f to the k. But why is it regular? Do you know? Have you seen this? What's the determinant? Okay, so that's the determinant of the Van der Monde matrix. I'm not sure if it's I smaller or I different than, so I'm not sure, but either way. And because the xi's are distinct here, right, this is never 0. And that's the determinant of this matrix, making it non-zero. And so it's non-singular, and that's it. Questions? Okay.
It's important for it to not be singular, so we will have one solution for every A.
Exactly. If it had like deficiency in rank, it could have been like f to 1 or something.
Okay.
So let's see one example of using this. So we are going to construct a worth PRG for decision trees. It's kind of funny, using k-wise independence. Just to show you the idea. I mean, it's worse. It's not going to be better than what we did. So say you have a size m decision tree. Okay, so m leaves sitting here. And you know what? Maybe the leaves are actually like that. like Itai said. And it's not clear what's k-wise about this thing, right? I mean, it's not there is no k, and it's like you can take m-wise independent, but that's way too much. Like, so the idea is the following: the idea is k-wise independent is not going to fool this tree unless k is huge. The idea is to look at the depth exactly. So I'm going to choose a parameter k. We'll choose it later, but I'm going to set some parameter k and to truncate the tree at depth k. But I'm going to do it in two ways. One in which we will lower bound the function, and one in which we will upper bound the function that's actually been computed. So if this function is f, I'm going to define f low and f lower and f upper by putting zeros whenever I truncate. And here I'm going to keep the value as is, whatever it was. So this is f low, and f high I'm going to put ones, like accepts. Right, so you agree that, point-wise, f of x is at least fl of x and at most fu of x. Because, I just gave up after I get to depth k, and I either put a lower value or upper value, depending on the function. But the point is now, what can you say about k-wise independence and these functions? And the lower and upper sandwiching functions. Do you think it's a good PRG for these functions? Right, if the depth is k, it means that I'm summing ends, and each end is on k variables, right? Maybe negation. So every end is fooled by the k-wise independence, and therefore their sum is fooled by the k-wise independence. Right? Every end function here is completely fooled by k-wise independence, and when I'm summing things, I should aggregate the errors, but the errors are zero. So I'm completely fooling k-wise independent completely fools decision trees of depth k. Right? It actually fools completely FL and FU. And because of that, if you give me just like 2 more minutes, then I know that it also fools F. So let's see. So let's denote the distribution k-wise independent by D. So the expectation of F given D, well, on one hand, it's bounded by because point-wise, FU upper bounds F, regardless of what D is. I mean, that inequality holds. And now I know that this thing is actually fooled. FU is fooled by the k-wise independence. So the k-wise and the uniform is the same for it. And that's smaller than the expectation of F of U plus, can you see what? What penalty should I pay in order to go back to F? What's the probability for me to... So F and FU differ exactly when I'm truncating. So what's the probability I reached a node that's truncated? So it's 2 to the minus k times m, right? I truncated at most m, there are more leaves than internal nodes. I truncated at least at most m nodes. Each of them have probability 2 to the minus k according to uniform. 2 to the minus k to each. So really, I can bound f of u by the relation between f and f of u using this. Anyhow, and similarly, you can bound from below, just using f lower by that. And using these two, right, this and that gives you that error is at most maybe twice 2 to the k times m. And if you want the error to be epsilon, if you call it epsilon, then you see what k you should take. You should have taken k, which is log m over epsilon, more or less, and the seed length is, it's k log so what's the hash functions are going from, k log n, which is log n times log m over epsilon. It's a worth dependence. Before we had a plus here using epsilon bias sets, now we have times. But I just wanted to show you this technique of sandwiching, that your function may not look like something that k is full, but if you can sandwich it by functions that you can fool, regardless if it's using k or not, you also know how to fool this function really in the middle, as long as they are close together. And they are. Okay, so that's it for now. Itai will talk about expander codes in an hour. Next week we'll continue a little bit more about talking about k-wise independence and more stuff about PRJs. Okay. See you next week.